And the way that we're going to learn these embeddings is by matrix factorization. To see how we can use matrix factorization to do object recommendation in the collaborative filtering setting, first we need to know what the data structure should look like. So what we're going to assume that we have is a matrix of ratings. So we're thinking of ratings of users give to objects in this case. So imagine that we have n1 users. In that case, we will have n1 rows in our matrix. And imagine that we have n2 objects. So they could be movies or books or what have you. We have n2 objects. Each object now has a column, and so we have n2 columns in our matrix. We'll call this matrix M. And now the ijth entry in this matrix, Mij, is going to be the rating that the ith user gave to the jth object. So this element in this matrix says that user I rated object j, and then the number will say what the rating is. So notice that in this case, this matrix has very many missing values. Because if each user can only rate a tiny fraction of the products, then there's going to be a very small fraction of values that we have in this matrix. So what matrix factorization does is it now tries to learn a low-rank factorization of this matrix using only the data that we've observed and ignoring the data we don't have, and then fill in all of the missing values in this matrix. And so when we fill in the missing values, those are like predictions for what a user will rate an object. And then we can use those predictions to make recommendations, because if we predict that a user is going to rate something very highly, we're going to want to recommend that thing to the user. We've already seen an example of a matrix factorization before. We didn't go into too much depth about it, but we discussed the singular value decomposition. There we saw that any matrix M could be decomposed into a product of three matrices. So in that case, the matrix M had no missing values in it. It was n by d. And we could write this matrix M as a product of a matrix U that has orthonormal columns. So the dot product U transpose U is equal to the identity matrix, times a diagonal matrix S that has zeros on the off diagonal and non-negative values on the diagonal, times another orthonormal matrix V transposed, meaning that V transpose V was equal to the identity. So we can always do this. What we didn't really discuss in detail is that when this, if M is a low rank matrix, what that means is that this decomposition, for example, if M is rank R, this decomposition will have only R columns. So if we can write M as a product of low rank matrices, then we don't have an n by n matrix here. We have an n by R matrix where R is less than n. So when the rank R is smaller than the minimum of the number of rows or columns, when it's much smaller, then in a sense what that's saying is that the matrix has fewer degrees of freedom. So a low rank matrix factorization can restrict the degrees of freedom of how many different types of things we can model in the matrix M. So this is going to be what we exploit, this idea of a low rank matrix factorization in the collaborative filtering problem. So specifically, what we want to do is we want to say that our ratings matrix, so this is from before where we have n1 users and n2 objects, and the ijth entry in that matrix says what user I rated object j. So this matrix, which now has a lot of missing values, is approximately equal to a low rank matrix, a matrix product with rank D. What that means is that we can take this matrix and represent it as a product of a matrix that is n1 by d times a matrix that is d by n2. And now d is going to be much, much less than n1 and n2. So if you imagine that we have hundreds of thousands of users and tens of thousands of objects, this will be a huge matrix, but d is going to be something much smaller, so it'll be something on the order of 10. That'll say how many degrees of freedom we really have in this matrix. And intuitively, you could almost think of it as saying how many things are really taken into consideration when giving a movie a rating. If d is equal to 10, then that's like saying there are 10 underlying things that factor into a particular person's rating of a particular object, but we aren't going to define meaning of what those are. It's a latent sort of thing. Okay, so we're going to assume this sort of a factorization, and we're going to call this matrix U and this matrix V. And now notice that the ijth entry in this matrix can be viewed as the ith row of the left matrix times the jth column of the right matrix. So this is the rules that you have with matrix products, that if you look at the entry ij here, that's approximately going to be equal to the ith row of this matrix times the jth column of this right matrix. And so now our goal is to learn these two matrices. And notice that if we restrict our view to the ith user, then what we're doing is restricting our view to the ith row of this matrix. And if we want to know what are the ratings that the ith user gives to all of the objects, we're going to take the ith row of this left matrix, call that UI. So this is a d-dimensional vector that's on the ith row of the left matrix. And then we take a dot product of this ith vector with any particular column in the right matrix in order to predict what the ith user will rate that product. And similarly, if we want to focus on a particular product, like the jth product, and we want to look across users in this way, then in that case, what we're doing is we're taking the jth column of the right matrix, call that VJ. That's also a d-dimensional vector. We can view this like the location of the jth object, and then we take the dot product of that vector with any particular row according to which user that we want to query. And so these are the locations that we're going to give. The ith user has a location in dimension in RD. It's equal to the vector UI, which is the ith row of this matrix. And the jth object has a location in RD, which is equal to the jth column of this right matrix. Now the question is, why does low rank work? What do we gain by being low rank? I'm just going to go through some of the intuitions here about why we would want to do a low rank matrix factorization. To see this, imagine that we have two movies. We have the movie Caddyshack and we have the movie Animal House. And so the movie Caddyshack corresponds to this column. So this is the column for Caddyshack. This is the column for the movie Animal House. And every other column corresponds to some other movie. What this column now is going to have is all of the ratings that any user has given to Caddyshack. So if there are n1 users, a subset of those users have watched and rated Caddyshack, and their ratings are going to be in particular rows of this column vector. And we have the same exact thing with Animal House. We have n1 users, a fraction of them have seen this movie and rated it, and their ratings also fall along the corresponding rows of this column. And we can imagine that some of those rows are going to overlap. The same user will have watched and rated both movies, but also some users watched one movie and rated it while not watching the other, and vice versa. Now, if you know about these movies, you know that they're very similar. They're from the same period of time. They're both the same type of comedy movie. And you can imagine, although it's not necessarily always the case. You can imagine that if somebody really likes the movie Caddyshack, they're also going to really like the movie Animal House. So I tried to pick an example that everybody would agree with. And therefore, if a person rates Caddyshack highly, they're also most likely going to rate Animal House highly. On the flip side, if a person hates one of the movies, they're also very likely going to hate the other movie. And so we imagine that the ratings along these two columns are very highly correlated. They look very similar to each other. That's what we imagine. And if you don't like this example, you could imagine a different example of two other movies that have high correlation in their ratings. And so what low-rank factorizations do is they strictly enforce this type of a correlation. So if we look at the column for Caddyshack and Animal House, and we have a rank D factorization, what we're saying is that this column is equal to this d-dimensional vector times this matrix, whereas this column is approximately equal to this d-dimensional vector times this matrix. And so in that sense, because we're restricting all of the objects and users to live in this d-dimensional space, we're restricting what types of matrices that we can learn, and we're forcing there to be correlations. And so because we're only going to have a very tiny fraction of the ratings in this matrix, by enforcing this type of a low rank, high correlation factorization, we're going to be able to borrow information across movies in order to learn these locations. So we're going to be able to borrow information across the users that rated Caddyshack in order to help predict what those users would rate for Animal House, and vice versa. And we're going to actually take into consider all of the correlations among all of the movies in making these predictions. The technique we're going to discuss in this lecture is called probabilistic matrix factorization. This is one particular model for learning a low-rank factorization in the missing data problem. I want to add a few bits of notation for this model. So again, here's our data matrix. We have n1 users and 2 objects. The ijth entry of this matrix is the rating of user I for object j. We'll call this matrix M. Now again, this matrix has very many missing values. So what we're going to do is let the set omega contain the pairs of all of the ratings that we have. So the pair ij is going to be in the set omega if mij is measured. So this set now has all of the measured index pairs in this from this matrix. And let's let omega sub ui be the index of the set of all objects rated by user I. And let's let omega vj be the index set of all the users who rated object j. So this is just for notation, so we can have a cleaner way of writing this later. What probabilistic matrix factorization does, what this particular matrix does, is assume a generative model, which is why it's called probabilistic. It assumes a generative model for the data that goes like this. So for each of the n1 users, we assume that their location in RD is going to be generated from a zero mean Gaussian with some covariance. And for each of the n2 objects, we're also going to assume that their location is generated IID from the same Gaussian. So this is just a simple case of what types of priors we could use. So these are the priors that we define on the respective locations of all the users and all of the objects in RD. And then given these locations, when we want to generate the rating, the value for mij for each pair in our measured set, what the model assumes is that this rating is a Gaussian random variable with mean equal to the dot product between the user location and the object location that we're generating the rating for, and some variance. So this is the data level distribution, and this is the prior on all of the model variables. So there are a couple of comments about this model. First, notice that since Mij is going to be assumed to be a rating matrix, in cases where it is a rating matrix, it's clear that this Gaussian assumption is wrong because the ratings are discrete. They take values 1, 2, 3, 4, 5, whereas this Gaussian is a distribution on continuous valued random variables that can take any value. So this is a bad model definition in the sense of being defined on the support of our data. However, in practice, it's going to work very well, and it's also been refined and developed. I just want to present the original model to you here. In practice, even though we make a bad assumption about the distribution on our data, it's going to work very well, because even though the data can only take one of, say, 5 or 10 values, they're still ordinal, meaning that order matters. 1 to, the relationship of the rating 1 to 2 and 2 to 3, in a sense, means the same. 1 and 2 are the same distance as 2 to 3, and 1 and 3 is twice the distance. So intuitively, that makes sense. And so this Gaussian is going to be able to still model that relationship correctly.